When we were checking the datasheet of the MOSFET in the previous video, we came across the safe operating area of the MOSFET. This time we are going to know what SOA is and why is it so important for our MOSFET selection. So let's start. This safe operating area is a graph, and if you see this carefully, it shows some boundaries on a body plot which consists of voltage, current and time. This graph tells us how much power this MOSFET can handle in this saturation region for a particular amount of time. On this x-axis, we have drain to source voltage, and on the y-axis, we have drain current. There are some limitations inside this boundary for some pulse duration. These values are being measured by the device manufacturer by testing MOSFET to its fullest capacity. So whenever we want to select a MOSFET, we should go through its safe operating area, which clearly shows how much power this little guy can handle. Because MOSFET dissipates a lot of power in many applications such as motor controllers, inverters and SMPS. Basically, this graph indicates the robustness of the device. That means when we're using the MOSFET at a certain voltage, then we should take care of the current and time period for which it is turning on. If it goes beyond that, then there are high chances that a MOSFET fails, and when it fails, it shorts all drain, gate and source terminals, which is very dangerous for a system safety point of view. Well, before moving forward, we should know what is the saturation region of the MOSFET. We all know MOSFET works in three regions, which are cutoff, linear and saturation. If we see an N-channel MOSFET characteristics, this is the cutoff region where MOSFET is turned off. This is the linear region of the MOSFET, which is also called as an ohmic region because MOSFET acts as a constant resistance independent of the VDS. This is the saturation region where we give sufficient gate voltage to the MOSFET to properly turn on. I have already mentioned in many of my previous videos that we use MOSFET in the cutoff and saturation region if we use it for the switching application. Now, coming to the SOA of the MOSFET. We'll take an example of the MOSFET BUK7Y3R5-40H. We have already seen the important parameters of the MOSFET in previous videos. There are 5 parts of the SOA which are very crucial parameters for a MOSFET and its boundaries are defined by them. We have seen the importance of the Rdson, dependency on current limitation, breaking down at some drain to source voltage, it's too hot to handle attitude, that means its thermal instability limitation, and finally, its great power which comes with greater responsibility. The first boundary is defined by the Rdson of the MOSFET, which is called as the Rdson limitation. This is the positive slope which is linear and it represents the basic Ohm's law. R is equal to V by I, which tells us how much maximum current can flow through the MOSFET, where the Rdson of the MOSFET stays constant. Next limitation is given by the current, which is around 500 amperes when you see it in the graph. But if you see the datasheet of the MOSFET, its continuous drain current carrying capacity is only 120 amperes. Then how does it go up to 500 amperes? Well, we are forgetting the peak drain current which we measure for 10 microseconds or lower. For this MOSFET, it is 526 amperes. Hey look, this outer boundary is also measured at 10 microseconds. And the DC limit of this graph is also given here. If you see this tiny flat line, this shows the DC current capability of our MOSFET, which is 120 amperes. Next limitation is the maximum power limitation. This is the constant negative slope. It represents the constant power, that is P is equal to voltage into current. This is the package or sizing limitation of the MOSFET. The smaller the package of a MOSFET is, the lesser its power handling capacity will be. Now the fourth limitation is the thermal limitation. Well, this is very crucial parameter because all of the other limitations are either known or we can calculate them. But thermal instability limitation is hard to calculate or predict, and we don't know whether the calculations are proper or not. So this has to be tested. To understand this term, we need to learn about the thermal coefficient of the MOSFET, which is change in the current with respect to change in temperature of the MOSFET. When we look in the datasheet, we find the transfer characteristics, which shows the relationship between gate to source voltage and drain current. This relationship is given at different temperature ranges. This is called as the zero temperature coefficient, where behavior of the MOSFET is same at all temperature ranges. Beyond this point, the increase in VGS has no impact on drain current. Well, we studied that MOSFET is a positive temperature coefficient device, but only before this point. Once this point is passed by, the MOSFET acts as negative temperature coefficient device. You see, when the junction temperature reaches 175 degrees Celsius, and even if you provide more and more VGS, the drain current doesn't increase. So, there is a temperature instability in the MOSFET which gives us this limitation. The fifth limitation is the breakdown voltage limitation, which is simply the breakdown drain to source voltage of the MOSFET, which is mentioned in the datasheet. This device can work up to 40 volts, so this limitation is shown up to 40 volts DC. Now the limitations which we are looking in this graph decide in which condition MOSFET will work. There are different boundaries and these are drawn at different time periods which a MOSFET can handle. The outer boundary is maximum RDS on limitation, then the current limitation, power handling capacity limitation, and finally the breakdown drain to source voltage limitation. This boundary is derived at 10 microseconds. That means if the MOSFET is used only at pulse timing of 10 microseconds, then the MOSFET will work within this area without exploding like a grenade. If you go further as the pulse duration increases, its operating area also decreases. Here, the pulse durations are 100 microseconds, 1 millisecond, 10 milliseconds, 100 milliseconds, and finally at the DC stage. That means the MOSFET will work without damaging in this area when it is working in the saturation region as a constant switch when it is turned on. I hope you got all about the safe operating area of the MOSFET. Next time, we'll see some more interesting stuff about this. Till then, stay tuned. I've added all the reference on this topic in the description. I hope you got something from this. If you haven't, you can watch the video again. Still, if you don't, you can ask your doubts in the comment box below. Hit the like button if you like this video, subscribe to my channel, and finally, thanks for watching.